Okay, let's do question 4. And question 4a, this is from chapter 23. And so one thing we do know, though, is that we know aldehydes and amines can react to form imines. What we don't know is how we can reduce them further, and that'll be talked about more in chapter 23. Okay, let's go to B. Here we've got sodium ethoxide. We've got a carbonyl with 2 sets of these alpha CH bonds. This carbonyl is symmetrical, so they both could form. Let me just draw the mechanism out. We're going to deprotonate one of our alpha CH bonds, and then we're going to form our enolate. And on your exam, it's worthwhile to kind of think about this mechanism, or you might kind of doodle most of it out just to make sure that you're getting the right answer here. I know I always like to draw things out. So when I redraw something, I keep something the same. Whoa. There we go. So here I've got my carbonyl, and then you can count carbons if that helps you. So we could do, doesn't really matter. I'll just probably start here, this one at 1, and then 2. Oh, well, maybe I didn't need to do that. But it might help you. If this is 1, I know that this one is bound to 2. Carbon 2 has an O minus. Carbon 2 also has an OET. Carbon 2 also has a hydrogen coming off of it. And so now what do? We're going to push this down. Use red. Whoop. There we go. We're going to push this down. Where's our good leaving group? We have a hydrogen, we have a carbon group, or we have an OET. Well, we're under basic conditions, so this is going to be an OET leaving. Notice I still have equilibrium arrows. And here, this is what I have. Now, I have a question. This center here is chiral, so that means that I will actually have both products form. And the reason is because we know the enolates are flat. So this enolate here is flat. It can attack on either side of this carbonyl. On either side of this carbonyl. So if it attacks at the bottom or the top, this enolate will either add this aldehyde at the front or the back of this compound, the way that we're drawing it here. So you're going to want to draw both. You'd imagine that this proton here is actually very acidic, right? Probably pK of around 9. So you'd imagine that would get deprotonated and hang out until it gets protonated to the product. You could see some side reactions. However, for this reaction, you would say that these two are your major products in about a 1-to-1 ratio. All right, this next one is also in chapter 23. This is the hydrolysis of amides. Now, we have talked about the reactivity of an amide, but you can imagine that this carbonyl can be attacked under fairly harsh conditions. This would be fairly harsh to get this reaction to go, but you would end up attacking with water. You would protonate your amide, and then you would get the corresponding carboxylic acid. I will not be asking you this for the exam on Monday. Let's go to the next one. This one's also in chapter 23. All right, here we've got another carboxylic acid derivative. We've got lithium aluminum hydride. We've got an acid workup and then a basic workup. Here we know that we can reduce this amide into the amine. When we do this, though, we know that we need to have both steps of our acid and then a basic workup in order to get the neutral amine that we want. This was fair game on your last exam. Here, let's go to the next one. This one's from chapter 21. This was something that we've seen on our exam as well. Here you're looking at an anhydride, and then you have two potential OH groups that could react with the anhydride. We know anhydrides are extremely reactive, maybe not as reactive as an acid chloride, but very reactive. We have two potential OH groups. Which one is more nucleophilic? The way that you decide which one will attack the anhydride is you look at resonance. Whereas we do have a resonance that this OH is sharing within the benzene ring, this carboxylic acid is sharing with another oxygen. We know oxygen is very electron withdrawing, and so this resonance form is actually going to tie up the electrons of this OH of the carboxylic acid more than this OH of the phenol. So that means that these electrons of the OH of the carboxylic acid are less able to act as a nucleophile. They can't attack as easily. They're tied up in resonance with the other oxygen. This tells us that the phenol will do the reactivity here and will act as the nucleophile. Here I can attack the anhydride. I can push up. Again, you don't have to draw the mechanisms for these. I don't know. I'm wondering if maybe it'll help someone. And maybe you guys are like, this is easy, Kelsey. We got this. I don't know. Hopefully it helps someone. It's okay if you already have it and don't need it. I thought I'd throw it out there because I know these things can get tricky. This one's positively charged. What I'm going to do here, we're under neutral conditions. Actually, the mechanism isn't the most important. What you need to do now, you can deprotonate this OH group here. Okay, now we have a neutral species. Then what I can do is I can push these electrons down. And then I can kick out this acetate. And then the product that we'll end up having is this acetate protected phenol. Okay, let's go to the next one. This one is the Gabriel Synthesis. Again, chapter 23. I have the which questions listed under your unit practice exam, unit 3, which ones are from chapter 23, but this one is the Gabriel Synthesis. We'll learn about this very soon. This one's also chapter 23. Cool. Let's make an enolate. In this question we have sodium ethoxide. We've got two very acidic CH bonds. These are alpha to 2 carbonyls, about a pKa of, I don't know, 11, 12. What we're going to do is we're going to deprotonate these. Let's take one of them here. Notice how I didn't even look at the other reagents yet. I just know that I'm going to make an enolate. So in my head, I just kind of like to move stepwise. What's next? So we got this one done. I always like to go stepwise. Say, okay, I did that one. Let's do the second one. I've got an alkyl bromide. I'm going to draw this out here. Specifically, I have a benzylic bromide, and we talked about this in our last exam, how benzylic bromides are more electrophilic than alkyl bromides. Here I'm going to push the oxygen negative charge down on the enolate, and then I'm going to attack. I'm going to do an SN2 reaction. In this case, we won't be reversible. Okay, got that one done. Now what do we do? Well, I have sodium hydroxide and H2O. What could happen here? Well, what will happen here is we can turn both of our esters into carboxylates. That's correct. Very good. We've got this OH minus. They're going to attack both sides. We have two esters here, these ethyl esters. They're both going to turn into carboxylates. I love this question. Here we go. So we just did this step. Let's do the step 4. What happens step 4? They get protonated. Okay. All right, we've got step 4 done. What about step 5? What does step 5 do with heat? We have a special kind of carboxylic acid here. This is a 1,3-dicarboxylic acid. The way that this is positioned is you can do a decarboxylation reaction. I can redraw this and I can show you real quick how we lose CO2. Okay, so under these conditions, I'm going to deprotonate here. I'm going to push down to make a new oxygen-carbon bond. This is an OCO, 2 double bonds on each side. This carbon now has 1 too many bonds. It needs to lose 1. So I'm going to push here, make a double bond, and then I'm going to kick back up. Now what do I have here? Oh wait, hold on. I didn't have to kick that one back up. If I do this, excuse me, I made that too complicated. This first one, we're actually going to use this double bond to grab that hydrogen. Sorry. So here I'm going to grab the hydrogen, push this down. See, it's an OCO bond. I've got 2 double bonds. That's my CO2. This carbon here picked up another bond, so it needs to lose 1. So that's why we push this over here. Essentially, we have broken that CO bond. This is a decarboxylation reaction that we've seen before. And the product that we have from this is an enol, actually. It's an enol of our carboxylic acid. And so now all we have to do is we will tautomerize this into our product. I've got 2 carbons here in between, and there we go. That's our product. Notice how I went stepwise. I think it would be really hard to look at this and do all of them in your head, so I think going stepwise is helpful. This next reaction, part of it is actually in your chapter 23. This part is in chapter 23. However, this is not. We know that this will make one of my favorite acid derivatives. I love these things. And acid chloride. Acid chloride, we know these are very reactive. What conditions, here's a little bonus question, would you need to get to this ketone? Acid chlorides can react with you remember they can react with cuprates. So I've got 3 carbons I'm adding. 1, 2, 3. That's a 3. That's a 2. So 1, 2, 3. Remember that cuprates have to have 2 equivalents of the R group. Don't forget that 2. Typically have a workup step here. There's a little bonus question for you. That would be something that would be fair game for the exam. Oh, did I